Is it working yet? Ah, yes, thank you. All right, welcome back to our second session of the TestVis workshop. We're going to start off with a keynote from Danielle Fisher. Danielle is a researcher and designer who works with users to best help them understand and act on their data. He was most recently a principal design researcher for Honeycomb.io, where he was helping site reliability engineers understand their complex systems quickly and clearly. Before he started at Honeycomb, he spent 13 years at Microsoft Research working in human-computer interaction in data visualization. So take it away, Danielle.
Excellent. Thank you so much. I'm glad to be here and will do my best to make this work virtually. I'm delighted to have been invited to the conference. I believe this talk came about in part because you and I were chatting a few months ago and realized that there's these interesting overlaps between the way that the visualization community thinks about their data and the way that, the way that the test community thinks about their data and some of the challenges that we are running into at Honeycomb, thinking about, understanding what's happening in production. So, as she said, I was the principal design researcher at Honeycomb.io until about a month ago. I am now taking a break and figuring out my next steps and enjoying unemployment. But I still thought it was a great chance to spend a little time talking about some of the fun things that we were working on, and to talk specifically about the work that we were doing to support the idea of understanding production. The interesting thing for me about being in this corporate space is that we've got these new design constraints that we don't necessarily see in other spaces. As our developer relations person, Jessitron, said, she thinks of our work as constrained by capitalism as well as user delight. And Honeycomb has always had a feeling about the importance of testing in production. What do we mean by testing in production? It doesn't just mean either running A/B tests on the network, nor does it mean that hey, everything's fundamentally unreliable, so you might as well be in production. It's fundamentally noting that the goal of test is to simulate production. Production tends to give you extremely hard to predict environmental effects. Things like things that your users get excited by are really hard to simulate. The strange paths that they'll take through your system. There's also complex interactions. Today's online systems are based on things like running Amazon clusters that talk to each other through Kubernetes and Kafka and dozens of other infrastructure tools that all might have strange interactions, under-known traffic limits, or that do unfortunate things to your data packets as they move around. So we strive for the idea of thinking about production as simply another stage of testing. That means when you think about this test in prod as a theory, it means that rather than trying to hold up production as this precious, beautiful thing, the place where code can't possibly go wrong, we instead think about it as a place where it's fairly easy to experiment, and that means to undo changes, where you can try something and see if it works, and if it doesn't, bring it back up and do it again, but right this time. And that also implies the idea that you have to be able to understand how your system is working so you can do that. That brings us to what this Honeycomb thing is. In today's talk, I'm going to talk a little bit about the test and prod users that I was interested in working with, and we'll talk a little bit about the observability domain, which is what the company did. I'm going to talk about two different domain-specific visualization techniques that I think speak to this broader theme. One of them is a tool called Bubble Up, which helps us understand what's changed inside a system or where two different systems might be different. And then we're going to talk a little bit about our work to support service level objectives, which is a way of reporting on broader reliability for your systems, but also speaks to this idea of building systems that are robust to test. I bet we won't get time to talk about the Candy Crush story, so I'm just going to leave that as a teaser to give either an outline for Q&A or if someone wants to come talk to me later. The observability space is the broad area that's been emerging in the last few years of supporting site reliability engineers, SREs, and DevOps, that's people who work in both development and operations. This is trying to move away from an older model where code was written and thrown over a fence and somewhere else an ops team deployed it out to a server. Instead, the person who writes the code is responsible for making sure that the code stays alive, and that everybody else who was on the team is responsible for helping make sure that things are working well and see how it's going. There's long conversations to be had in other contexts about pager rotations and who supports when and what sort of training you need that aren't really as relevant, except to say that we expect the operators that we're working on to be a great deal more sophisticated than either like running shell scripts or turn the system on and turn the system off and turn on again. But instead, we expect them to have a deep understanding of what the code's meant to do and how it's performing, and to be able and empowered to change the code to be able to fix things. This fundamentally turns our users into a sort of Sherlock Holmes. When something goes wrong, and things often go wrong, they need to go out, figure out what happened, and figure out why it happened. And if it's in 2 a.m, they want to be able to figure out how big an impact it was so they can go back to bed. The tools that are traditionally used for this are often come with keywords like monitoring, logging, and tracing. The broader story that I want to tell, though, is this idea that there's this exploratory analysis. We sometimes talk about the mean time to WTF. How quickly can we figure out what's gone wrong? I'm going to quickly flip over then and do a very quick demo. We are looking at a hypothetical website somewhere, and it's got a number of requests coming in, and they're wiggling along, and we can see that it's running a fairly steady 90 to 100 milliseconds per query. Things look good. Someone comes in, they click on something, it works okay. Or sorry, we're seeing a constant 90-something requests per second. I misspoke. We can also see over here the duration of requests. And things were doing pretty well, running about 800 milliseconds at a time. And then something happened at 1 o'clock, which is that requests began to get a little bit slower. Not all of them, but this is the 95th, this is the P95, the 95th percentile. And they started getting slower and slower and slower, and then they sped up again. So we might ask, what made this world a worse place? How many users were affected by this slowdown? Was this one person? Was this many? How much impact did it have? Like, you can imagine that if we're looking at the site beginning to run at 2 or 3 seconds at a shot, that might mean that people might get discouraged and stop taking sales. So traditionally, what you might want to do now is start breaking this down by something. So for example, I might say, you know what? This might be related to, the Kubernetes nodes that I'm using. So I might search on K8's node name, and unfortunately, it turns out that everything's on the same Kubernetes node. So that's not it. Well, I could also try, I don't know. It's going to show up on Kubernetes. Sorry, I had a couple fields ready for this, and maybe I might check specifically whether the HTTP method that's calling this is affecting it. And well, that does seem to be causing a difference. We can see that post commands seem to be affected by this, but get commands aren't. But that's still very general. And I'd have to keep searching through more and more fields, trying to figure out, maybe it's the country the user's coming from. Maybe it's, the activity they're doing. There's lots of possibilities. But still, you can begin to see how this sort of approach would at least begin to tell you how much traffic there is, what the different fields are, and so on. This is a classic data visualization sort of problem in that we've got a couple of different fields that users are trying to interpret. And you can see that we're working on a system that's able to take in high dimensionality. We've seen, hundreds of fields here. We've got, we're coming in with a fairly high cardinality on our values. Some of these fields are go down to, oh, there's user ID, and you can imagine there might be hundreds or even thousands of those. And it's high volume because we've lots of data coming in. So what we wanted to do is figure out what approach we can use to, help both enhance this experience, because, despite the fact they've sort of outlined some negatives of like places where this fails, the really nice thing is we do have this great database engine. We've got this ability to query, and, we were selling this very happily as a product, and users were pretty happy. But what we found as I started watching what users were doing, is that our users were not, passive consumers. They really want to explore data. Also, they're not Viz experts, and that meant that like some of my first impulses, which give them some GG plot bindings or some D3 bindings, let them build their own visualization, isn't going to be enough. We have to actually have some opinions about what to show them and why. We also had some nice powers. Like, it turns out that errors tend to be fairly redundant, and so being mostly right is okay. We're not looking for that, one needle in a haystack. So the state of the art as of 2018 or so was this process that I was just showing you, the repeated group buys. And we were getting pushback both from our users who said, why do I spend all this time jumping between group buys? Can you give me some sort of like magic group buy that groups by everything? And we also got pushback from sales who was saying, people don't understand why they want to send us hundreds of fields if they're just going to have to dig around in them later. Now, some of you may know Eugene Wu, whose thesis work on Scorpion was actually designed to solve precisely this problem. You select some data and it shows you why it's different. We didn't do it. We read the Scorpion paper very carefully and realized that the computational cost of that would basically melt the system down. However, we found that in our case, anomalous events tend to be pretty easy to recognize. It's not hard to find out why something went wrong. And the good news, it's not hard to recognize that something is wrong once you found it. In fact, we could summarize the SREs that we worked with as being anomaly detectors. Unfortunately, they're also constantly shipping new versions of the code that they release, and they're making changes and they're tweaking things. So any automated anomaly detector system would tend to fail because fundamentally the job is to be an anomaly creator. What we ended up doing was creating a system that allowed us to fairly directly allow users to express this question of what's different. So instead of showing you the 95th percentile of slow requests to this website, instead I'm going to show you a heat map. This is just our, classic histogram over time. At every time step, we've got a histogram, and we can see how that varies. And we can specifically see that 1 o'clock, as things began to get slower, there was in fact this little branch up here that's getting slower and slower. And you might want to ask, what's different about it? So we built a UI that allows you to select those points. And then we're going to do the simplest possible thing we could imagine, which is just take a sample of 1,000 points inside that box and a sample of 1,000 points outside that box and do comparative histograms. And some things pop out immediately. The single biggest to me is right here, user ID. Almost all these yellow dots up here are shared by one specific user ID, user 20109. That value has occurred many fewer times than, occurs almost entirely inside the selection and almost never in the baseline. We can also see that user seemed to be calling /cart/checkout and cart/checkout, and that almost everything else that they were doing kind of looks like all the other data. There don't seem to be major differences. This is pretty powerful because what we realized we can now do is ask, what in particular was this user doing? We know, by the way, now to send off customer success and go talk to someone and say, hey, either you broke our website, please stop trying to hack us, or ultimately, hey, we apologize for our website not being responsive. It depends, what we discover is going wrong. But we can also do things like go look at one of the traces that's specifically what's happening from user 20109. Sorry about that. And we can see the specific trace of one of these slow queries. This one, oh, interesting. I don't usually mention this one. Even when we look here, though, we can see, like, they called this cart checkout operation, which took 1.2 seconds, which was longer than we wanted. And when we scroll around asking in this trace waterfall view where that 1.2 seconds went, you can keep scrolling around, and the biggest chunk of it seems to have been this 456 milliseconds. That's almost half the time. And that is certainly more than explains the time between what usually happened. And here's this interesting thing. Checkout.discounts gets called 4 different times. I'm going to go pull, yeah, I know. I'm going to go pull another sample trace from there, from an even longer one, and go see how that compares. And what we see here is that the call to get discounts is in this weird repeating loop. So something is funky in our code. Something happened where the user tried to check out, and we called checkout.discounts in some sort of loop. Each of those calls took, 100 milliseconds, quite reasonable, but we seem to call it more and more and more times until it hit 2.5 seconds and the user clearly got frustrated and went away. We now know something about our code. We know that we're calling get discounts in some sort of weird loop. We know that the length of that loop is increasing, so we know what the developers have to work on. We know how many people were affected, 1 in this case, and we know how angry they are. That's a pretty impressive set of findings for one quick check overnight. So Bubble Up was this way of shifting our perspective on the data from the user direct, from being able to query and slice the more traditional SQL-like queries into this new perspective of slicing across the histograms. Now, there was a bunch of rounds of iteration, as you sort of might expect in a Viz kind of community. We had to put the ranking algorithm to decide what order to show them in, how big to make the bubble ups, that kind of thing. And there's still some pieces missing, right? The fact that I showed you how to use it inside a heat map, users have been asking for other modalities. There's also one other really interesting implication, which is that it really highlighted why you want high cardinality and high dimensionality inside our system. And it started encouraging users to send us more and richer data, which meant that we could in turn feed back to them more and better outcomes. Bubble Up also empowered us to move in a different direction, which is to start asking how services were doing. Our notion of service health for a long time was a very naive trigger. If a value is greater than a threshold, fire. If it takes more than 30 milliseconds, if it, fires an error, and users would say, hey, it's taking I set my trigger at 300 milliseconds, and now it hit 301, now it's back to 299, now it's back to 301. It keeps flapping up and down. It's annoying. Also, hey, my notion of what's normal keeps shifting around a little. Can you give me a flexible threshold that'll change? Can you give me a rate of change? And so we had a lot of different choices, and we spent some time evaluating. Maybe we want that anomaly detector I was talking about before. Maybe we want to move around thresholds. But then we started thinking about that conversation we started this talk with, this idea that production is really a form of test. And so that means that you should have the ability to say, you know what, I can tolerate some badness here. And so we built this mechanism called service level objectives. Fundamentally, what a service level objective does is it says, this is the percentage of events that I expect to be successful over time. As data comes in, then we're going to label each one as good or bad or irrelevant to the objective. So I expect requests to this particular subservice to take less than 500 milliseconds. Good is it took less than 500. Bad is it took more. Irrelevant is it was a request to some other service and we don't care about it. We can use that again to express, that's going to result us in a budget, the number of bad events allowed. And that budget's really interesting Because if you've got a lot of budget, then you can go off and go do a whole bunch of testing, try new things in the world, and you know that you're still going to be okay because things can't go so wrong as to blow your budget. Or you might decide that this is a very critical service and you have to watch it like a hawk. And so if that budget starts burning, you know to act on it very quickly. So we built a UI that essentially allows us to express how much of your budget has been burning down and where it's been burning down. So I can look, for example, at this chart and say, I've got this threshold of 99.9% events, so 1 in 1,000 can be bad. And over the last 30 days, I've burned down about 40% of it, which is great, right? That means I've got 40% left. That's a lot of space to go wrong. And in fact, it looks like much of the burn happened in like 2 mini incidents that each burned about 5%, which doesn't seem too bad. And because I'm maintaining that pretty good threshold, right now my compliance is pretty high. We can look at a system that's much closer to crashing, or that's much closer to running out. Here's a system that's at 1.19% of budget left. It's been burning pretty steadily. So we've got a pretty tight margin on this one. And we've probably got an alert going off right this very moment. In fact, you can see right here that we're predicting that it will be exhausted in less than 4 hours. So that's an all hands on deck problem. And it looks like some of the worst that happened was a little bit ago. We had a big plummet in the budget. The SOI was passing a lot less than we usually thought it would. Now, we are able to use this notion of good events and bad events to do precisely the thing that I was talking about earlier with Bubble Up. We can compare those distributions to each other. And so when I see, I can click over, for example, to the time period where things were bad and go look at it. I can see that some of the events were slow. You can see those dots at the top representing events that took too long on this heat map. We can also see dots in the middle, which means that they returned errors. So now we've got sort of a sense of what kinds of things were going on, which is that both it was crashing and the ones that weren't crashing were sometimes running slow. And we can scan through and go look. We can see the status code 500s that were the errors. We can go see that there we go, an invalid memory address. We can go see that moved us from giving the responses that we wanted of nice structured data into plain text. So we've got, and we can see that's interestingly because of this missing something or another. Now, when I look at an error and see that there's something called missing, that almost suggests to me that there might be bad input, not bad output. So that gives us a couple places, again, to go chase down, go look into the code and go figure out what might be producing that particular error and what happened. So that gives us this really nice notion of what it means to be using to be testing and to be controlling how much we're testing and how much unreliability we're allowed to introduce into our system. As an interesting side note, as we built the system, we said, okay, we're going to run this 30-day query to find out how we're doing over the last 30 days. We'll just run that once a minute. It turned out that we managed to burn $10,000 running that in just one day because all of our queries were running on AWS, and AWS, doesn't necessarily like you doing these massive queries that quickly. So we started a caching mechanism that crashed the last 29 days and 23 hours, then we only would requery once a minute for that last hour. That kept us going for a full year and a half. The challenge with being in a startup is that the company is on an exponential growth curve. And in early 2021, we started landing big customers. We're like, great, this tool is fantastic. Now, we are seeing sort of this jagged sawtooth pattern that you might imagine of like, the first minute of an hour, it only takes 1 minute, it takes milliseconds to run the query. And it gets slower and slower and slower as it looks at more and more data. And we saw the shark tooth pattern, and that didn't worry us. What did worry us is that the shark tooth pattern was getting slower and slower and slower itself. At some point, it would take us on any given instance of our server more than 1 minute to run that query. And the moment it takes us more than a minute to do a minute worth of computation, we're stuck. So we referred to that moment as a slow apocalypse. And the result of the slow apocalypse was actually changing how we did our queries from once a minute refreshes to putting them onto the ingest path where we could evaluate as data came in from our users instantly, are we acting on this or not? It was a substantial engineering effort, of course, to move that into the ingest path. But the major advantage to that was that it allowed us to start, was that it had this major efficiency. Now, what's really interesting is we had this moment of trading off, essentially, efficiency of our system for engineer time. And for quite a while, it made a lot of sense to save on the engineer time to continue to test as we were working on it. Once we knew what SLOs had done, we'd been using them for a year and a half, our sales teams were feeling good about it, it began to make a lot more sense to us to go through that engineering effort. And in fact, that worked. Once we made that change, as you can see, the total amount of time that we spent computing SLOs plummeted from, there you go, 1 million milliseconds at a time to a couple 100,000. Unfortunately, I don't have time right now to tell the Candy Crush story. As I said, I'm happy to talk offline. What I will do instead is I'll conclude and say that this idea of testing in production has both been a perspective that we've used on our users as we've tried to think about the way that they're getting to know what their data is doing. And it's also been the story of how we think about ourselves when I talk about rolling out the SLO system, building a little bit, running it, seeing whether seeing and beginning to be able to build something that we can prototype on, modify on, and even if it means spending more money than we otherwise would, be able to act on it, has been a lot of fun and a really interesting process. There's something very thrilling about pressing the button and then going on to switch to the deploy button and then switching to another website to go see how it's working. I think I'm pretty much out of time, so I wanted to switch over and maybe if there's a moment left to leave time for a question or two.
Right, thank you so much, Daniel. Okay, so as usual, we will look for questions in the Slido and also raise your hand, and I'm happy to bring the microphone over. While you guys are thinking up some great questions, I have this question, which is that, I mean, there's so much that the honeycomb system does, and I think we've seen earlier in the day that there are just so many ways to do testing and observability. So how do you decide what to prioritize first when you start building this system out, since you've been there for a while to see it grow?
That's a great question. To some extent, that's the job of a product management team to be able to evaluate requests coming in from sales side, from user requests, and then for things that users don't know they're requesting. So like the Bubble Up product that we saw was not triggered by people saying, I want to be able to do these massive comparisons. It came from them saying, I'd like faster queries. Honestly, this is a point of some contention, and I think it fundamentally has to be. There's going to be fights over that prioritization because there's only so much engineering time and there's a lot of cool stuff to be done. And it's a question of are you trying to make future users happy, current users more satisfied, or sales more excited about what they can sell? I don't know that I have anything more sophisticated to say that other than that it's, yes, a complex dark art that involves way too much politics.
All right, thank you. Is there any questions from the audience? All right, I have one more question, which is that when you were how are you telling how the users are adapting to these systems or beginning to use them? Is it a combination of interviews, logs? There's so many ways to do that as well.
Right. So one of the wonders of working at a company that builds a telemetry solution is that we were obsessed with being able to understand what our users were doing and how. So every click anywhere in the UI went into one of our telemetry sources where I used precisely the same sort of querying engine that I'm showing you to say, how many people are looking at, say, the trace view. And when they're looking at the trace view, what's the distribution of the number of spans in those traces? And how many of those traces have, more than 30 fields going across? And any question that you might want to ask, we could instrument. And in fact, very often the way that a project would get started is by having a conversation about what we expected a successful use of the product to look like, what sort of traps and holes we expected users to fall into, and then start instrumenting that stuff in advance so that as we are getting closer to release, we build internal dashboards of usage for this particular feature and then be able to go watch the curves pick up and adopt. So, for example, when we started when we released Bubble Up at first, we weren't seeing adoption at all because very few people used heat maps, and the people who didn't necessarily understand how to use it. We decided for that project that the right approach was to start working with customer success and our new customers to train them on heat maps and Bubble Up from the very early stages so that they could, and we'd see someone would go off and do a training and suddenly the usage numbers would spike. And then most importantly, we'd see that those spikes would stay consistently high for weeks or months. Those people would have learned this thing and now they had a new tool and they were using them. And so that was, so we were able to reflect on our usage by tracking ourselves.
Okay, that's really exciting and fascinating. I think we're about out of time. Thank you so much for being here. I will chase after you about Candy Crush some other time.
Excellent. Thanks so
again.
much.
Okay, so now I'm going to switch over and Daniel is going to share the papers.
Welcome everyone, my name is Jacob and I brought you the paper Test Intelligence, How Modern Analysis and Visualization in Team-Scale Support Software Testing Today. In my business life, I work for the company CQSE. That is short for Continuous Quality in Software Engineering, and one thing I do there is to support teams in their development efforts and testing activities by using data the teams already have. This is also where we land the term test intelligence from. So it's not related to artificial intelligence or machine learning. It is from the term business intelligence, where you have some data sources and you do data analytics to find out how your company basically works. Today, we will focus on analyses and visualization of those, use the version history from the version control system, tickets from the bug trackers or issue trackers, and test coverage from your test runs. Questions that can be answered from analyses that are within test intelligence are usually asked by testers or test managers and go in the direction of where are untested changes, because it is most likely that bugs occur there in production. Where do the most bugs occur in my software system? So are they all in one module or different modules? And can I take some countermeasures against those bugs? And regarding the test execution, are there maybe tests that are more valuable than others to execute right now? I brought you now some examples for the different data sources, and we will start with an example from the version history. So you might know this picture. This is a simple file diff. So same file in two different versions, and the differences are highlighted by a gray background. This is a low-level approach to view the changes, and I can take that to a higher level using a visualization. And therefore, I use a tree map right now. A tree map displays or visualizes a tree structure, in this case, the file and folder structure of a software system. And here, a large rectangle with a white border represents a software component, for example, a Java package. If I zoom in one step, I get all the files, all the classes of a system. And if I zoom in one further, I get all the methods. And the size of a rectangle here directly corresponds to the length of the method in terms of lines of code. And now I can visualize the changes by saying, from a given start date, If the method has not been changed, I want to display it in gray. If it has been changed, I want to have it in color. And I use orange for methods that have been changed and red for methods that have been added to the code base since the start date. Next data source is test coverage. You also might be familiar with it. In this picture, if you execute tests, you can record which lines have been executed during the test. And for this method I brought you, all lines have been executed but one. This is also a low-level approach to investigate code coverage. And I put that to an upper level by displaying it also in the tree map. Same tree map as before, or same tree map layout, but now the color semantic has changed. All methods in gray are methods that have not been executed in the test, and the green ones are those that have been executed in the test. Without a cool visualization, but for the sake of completeness, I brought you an example for the last data source, so a ticket from our issue tracking system. This is a screenshot from our Jira, and it has a ticket ID, it has a description or a title, then a longer description on what is the ticket about and some meta information. From the data sources to the actual visualizations. The first visualization I want to show you is the visualization of a system-wide test gap analysis. Test gap analysis itself focuses on showing you changes that have afterwards not been run in the test. Why is that relevant? Our intuition says to us, and also research has shown, that the probability that you will have a bug in such an area, so a changed yet untested area of the software system, is higher in production than for the other areas of the code. So we already have all the ingredients that you need for that analysis. So we have the changes tree map from before, we have the execution tree map from before, and to now get to the results of a test gap analysis, I just take the changes tree map at the bottom and lay the execution tree map above, ignoring all the methods that have not been changed. The results would look like this. So all the methods that have been changed and tested are displayed in green, and those that have been changed or touched and not been tested remain orange or red. And this analysis here revealed large areas of the code not have been tested after the last modification or addition to the code base. So in fact, this is not just a made up or fake system. This is a real software system right before the planned release. And we asked the team whether this is intended, that there are so many of the changes and additions not tested. And they told us that is not intentionally, but they had some innovation project where they wanted to add automatic tests, software tests to the project. And somehow there was a misunderstanding between the departments of the automatic tests and the manual tests that have been performed earlier. And somehow these areas were remained untested. They decided to shift the release based on that results and add another phase of retesting, and afterwards most of the test gaps were closed and appear now in green. Such a big tree map might be overwhelming, so it shows you a lot of information. If I'm just responsible for writing automatic tests for just one single issue, or if I'm the tester responsible to test a single new feature or bug fix. And I brought you an example. So how we develop today, it is not pure waterfall, but agile, and we work on different feature branches and release several times a year. There's the possibility to not view all the test gaps of a system, but to view the results just for a single issue. And this is how we apply that in our own development. So this is also a screenshot from our own development. You have in each row one single ticket. And on the right-hand side, you see a bar chart that says you how much test gaps is there still remaining. If I click on one of the tickets, I can also investigate where are the remaining test gaps. This tree map only shows methods that have been altered within that ticket. And we can do that by prefixing each commit that is done for one issue with that issue ID. The next visualization can reveal interrelations. And I brought you an example to show interrelation between coverage, code coverage, and fixed frequency. This tree map here shows you all the files of a software system And the opacity of the blue color shows you how often has this file been changed in course of a bug ticket. So we only counted bug tickets here. Tickets that were classified as feature tickets were not taken into account. And you see this middle area of the code base is somehow striking because it's much darker. And yeah, let's see how this looks like if we take this tree map here. This is the tree map of the line coverage, and also the middle area is striking, and white means a low code coverage, green means high code coverage. And if we take that over each other, both tree maps, it indicates some kind of interrelation. We also went this time to the team and asked them, why is that the case? And they told us that the middle area is standing for the UI code, and the UI code were not good testable. So developers wrote less UI tests as the UI tests were difficult to write. The project managers decided to invest additional time to improve on the testability of that code, and hopefully now also the fix frequency in the UI code is lower. The next visualization shows you how you can benefit from the test selection on the basis of code changes and coverage. If you have a test suite that runs over a long period of time, it might be good to select only the tests that run over changes, because it is most likely that those tests who run over changes will find bugs early, and you can also feedback to the developers very early that with their changes maybe some things in the system broke. To demonstrate that, I brought you an example from our own development. Those are the changes we have performed for one single issue. And to perform test selection, we need test coverage per test case. So not for a whole test suite, but per test case. And this is how the recording for one of our test cases looked like. I will now show you an animation that runs 30 tests per second. And each coverage from one test will light up in white and then fade out to green. And we will see how fast we will execute one of that changed methods. So when we look at that animation, we see some areas of the code lighting up more than once. So these are tests that, or these are areas that are covered by more than one test. But even if we have executed by now some 100 tests, the changes have not been covered yet. And the probability that we will find a new bug there is very low, since we have not run the changes. At the end, it was that we have had more than 4,000 test cases executed, but only 1, 2, 3, 4 test cases did cover any of the changes. And this is how the test selection algorithm works. We also use with some teams. We select the tests first that run over changes. Besides test selection, also test prioritization plays an important role when it comes to long-running test suites. And I brought you a visualization that shows you the benefits of test prioritization based on additional coverage per time. This chart shows you how the coverage evolves during the runtime of your test suite. So on the right, on the x-axis, you see the relative runtime of your test suite, and on the axis, you see how the coverage evolves. And in the normal execution order, you see a rather flat curve, and on the orange curve, you see an optimized run order, and there the coverage is gained much faster or increased much faster. So why can we do that? I brought you an example with the project Pixelitor, which is an open source drawing application implemented in Java. Also for Pixelitor, we recorded each test case one by one, so we have coverage for every single test case. And if one wants to compare the different test coverages, you will see that the first row here looks somehow similar, and the last row compared to the first row looks more different. In a normal test execution order, and you execute mostly tests in buckets. So tests that are testing similar things are run right after each other. And we see that also in Pixelitor. So we have different blur operators in pixelator that make your picture more unsharp. And the first one that would be executed is the Gaussian blur filter. You have the coverage of that test case here. The next test case executed is the test of the motion blur filter. And you see again the coverage of that test case here. But the blue methods are those methods that have already been executed by the first blur filter test. So if one would have introduced a bug in one of the blue methods, it's highly likely that the first test would have already detected that bug. And only the green methods here are additional coverage for that test case. This holds true for the next test case, the lens blur filter, also not that many green methods that are additional executed, and also for the smart blur filter. So if you want to optimize that, we can do it in a different way. So we select the test case first that covers the most methods in the system in the least amount of time. This would be this test case here. And next we execute the test case that executes the most additional methods in the least amount of time again. And you can see also here some blue methods are there, but the number of green methods is much higher. So you gain much faster your test coverage in your test runs. Also, the third test covers a lot of new green methods. This is how we can obtain coverage much faster in a test run. And in many teams, we see also the wish that they just want to have a clear cut. For example, like after 10 to 20% of the normal test run time, for example, just like 1 hour instead of 10 hours test run time. So this would be a clear cut here. And you see if you optimize your test run order, you would get more than 60% coverage. And for the unoptimized one, you would only remain with 20% method coverage. This is also an interactive chart. So if I select 7 seconds of runtime, I would get the results here for executing 3 tests. With 12 seconds, I see that I should execute 5 tests. And you can see in the chart above how much coverage you would gain with executing those tests. In the paper, we present additional visualizations, but for the sake of time, I only want to show them briefly here. We introduce you to auto-generated verification matrices. So for each requirement, we can answer with that visualization whether there exists a test that verifies that requirement, and if there is a test, whether it actually succeeds. Another visualization we show is if your test fails, you might be interested in which methods have been changed since the last pass of the test, as it's most likely that the failure of the test case might lay within the changed methods since the last pass. Last visualization, also just briefly, is the test selection of test cases that can close a current test gap. So this is the issue test gap tree map we have seen earlier, with 2 methods already covered and 3 methods that are test gap. And this method here on the right side could be covered by executing one of those 2 tests here. This was a lot of information in not that much time. If you have any follow-up questions, either today in the workshop or later on, just ask me, write me a mail, call me, and we will catch up. And I'm happy if you read the paper. And now I thank you for your attention, and I'm open for any questions. Welcome, everyone. My name is Jacob, and I brought you the paper Test Intelligence, How Modern Analyses and Visualization in Teams.
Now it's working. We tested it. Okay, should have tested before. Okay, I think there was one question, just quickly.
So, yeah, is the speaker hearing me? I'm not sure. Yeah, can you hear me?
Yeah.
Okay, wonderful. Yeah, thanks a lot for a very nice talk. I like the system, and I think it's great visuals. I was just wondering about the tree map approach. It's kind of a visualization which consumes a lot of screen real estate, despite it's a very sparse signal you're communicating, right? And in the light of the fact that the layout is not really like a one-to-one mapping to the code, I was wondering if you have thought a little bit in other directions to focus more on the things which are relevant at the moment and not always show the whole thing. Have you reflected on this a little bit?
Very good question. That was the second analysis I showed. There I reduced the overall system test gap tree map, which contains a lot of information, down to showing only the methods that have been changed in course of a single ticket. And so you have only like maybe 20 methods in average, and that is good overviewable, and the tree map is also interactive, and we have made good experiences with developers as well as with testers to use that kind of visualization.
Okay, thank you. And can you briefly comment on the size? I'm not sure, was that related to the lines of code per method, the size of each tile? Yeah, all right.
Yeah.
Okay, yeah, thank you very much.
You're welcome.
Thank you. I think there's one more.
I just have a question about whether you have any insight onto, or whether, like, from your analysis, you got any insight into what caused redundancy in the tests, and whether there was any way to mitigate that redundancy, or somehow, or whether it's like kind of baked in or necessary.
So you mean redundancy in terms of coverage?
Yes, in terms of coverage, exactly.
So, in fact, I think this is caused by the similarity of the test cases. For example, when we get back to the filter example, we have just like a ramp-up coverage that is needed to execute some filter methods, and we see a lot of redundancy for several filters. Does that already cover your question?
Yes, yeah, that's good. Thank you.
Okay, yeah, welcome.
Thank you, and I think there.
I saw one question in the Slido, which was about from Michael, who asked whether we also can use manual test coverage, and that is indeed possible. So the example from the first picture, the system test gap analysis, was coverage from manual test cases. We do that for a lot of different programming languages, and we can also combine coverages from different sources or test levels. So doesn't matter where the coverage stems from.
All right, thank you. I have some problem with Slido. I think there was one more question. Maybe, is that right? The training. I think there was a question about training. So do you require any special training for using this type of visualization? Maybe you can comment on this.
So we have a documentation about how the layout is structured. And usually when a new project or system uses that kind of analysis, we go with the teams and describe how to work with that approach, because with our experience, we know that it's not enough to just have a tool to measure some things and to display some things, but also to establish a process. And that is typically the point in time where we explain the developers and testers what this visualization, how it is built and how to use the information from that. So yes, typically we have some kind of ramp up or training, but that is very short. So when we onboard a new team, we typically require just like a 1-hour meeting.
All right. I'm not seeing any further questions here. Thank you again for your presentation and for the Q&A session. Thank you. And I think we can go to the last paper presentation, which will be pre-recorded as well.
Hello, my name is John Jacobson. I'm a PhD student at the University of Utah, and today I'd like to discuss our work on Float, a framework for workflow analysis and transformation in support of compiler-induced variability detection. So I want to start by discussing our goal to understand complex workflows, particularly in high-performance computing applications, which have complicated workflows of their own, often designed to be portable across heterogeneous systems and operate in highly constrained resources. And beyond that, when we want to analyze these applications, for example, with verification tools to verify, say, data race freedom or other properties, or to understand their performance with something like profiling tools, we're adding another layer of complexity. This complexity impacts the maintenance and development of tools, trying to pass these tools to new developers, the correctness of the tools, and also their adoption by new users. So we believe that more flexibility and transparency are needed in these kind of applications, and thus created Float specifically to support and analyze a framework called FLIT, so that it can conform to the needs of FLIT and grow with it more naturally as it's developed in the future. So before discussing Float, it's probably good that we understand what FLIT itself does. So FLIT is a floating point reproducibility test framework in the Pruner's toolset. FLIT functions by performing a multi-compilation search across as many different compilations and comparing the floating point results of these applications against a trusted baseline compilation to determine the variability. So numeric reproducibility across compilers is what we're looking for. It's something we want and often expect, but it's not guaranteed under different optimizations, even within the same compiler. Classically, compiling with aggressive optimizations like O3 and FastMath can give very different program results. Not related to bugs. They're not flaws in the compilers, but caused by the nature of floating point rounding error. Unfortunately, this is kind of a problem given our need for increased performance. How do we balance our need for more speed and performance for our applications and trying to ensure their correctness across any inputs and situations and more aggressive optimizations? So I want to look at one specific example of this type of variability that FLIT can identify, which is in Lagos, a Lagrangian hydrodynamics mini application. When compiled with the IBM XL compiler under the O2 optimization, and then compared to the same compiler under the O3 optimization, FLIT identified an 11.2% relative error, yielding a negative gas density. On the other hand, also provided a speed up factor of 2.42. So what happened? We want this kind of large speed up, but we can't tolerate breaking physical laws and the results of our application. So how do we identify the source of such an error? And of course, this is what FLIT is designed for. Provided a user application, in this case Lagos, the user defines and writes their own custom FLIT unit tests conforming to the FLIT test specification. These tests just mostly need to be deterministic, so that re-executing one of these test applications with the same inputs should always give the same output. But given these, FLIT can take any number of such test cases and as well as any number of compilation settings provided by the user, and execute and compare the results of all of the resulting binaries. And then this allows the user to analyze the variability and the floating point output as compared to their chosen baseline, as well as the performance increase afforded by the more aggressive compiler optimizations. So if in analyzing this data, the user finds sufficient speed up and a good compilation setting that does not cause errors with their program, then great. But more interestingly, what if to achieve desired speed up, our application is finding large variability that we can't tolerate, giving incorrect results, such as in our Lagos test case. So Flit Bisect can then search the user source application and assign blame for the floating point variability down to individual files and even functions in those files. So running Flit Bisect then on Lagos can identify one or more specific functions that are contributing to that variability, and the user can then apply standard debugging techniques to find the source using tools or manual investigation. And on modifying that source, we're able to optimize more aggressively without affecting the variability of the results of their tests. So benefits of Flit are, of course, finding that these compilations cause variability at all, but also helping the user understand the trade-off of this floating point variability with the increase in performance that they will get from different optimizations and compilers, and also can help identify specific functions within the source application that actually cause variability under different compiler optimizations. So why do we need tooling support for tools like this? You might imagine, as you may imagine, a tool like this has a quite large volume of activity. A bisection search of a large number, say hundreds of different compilation settings, along with any number of user tests being tested under all of those compilations, is a large amount of work for the system. And even with simple build system, we've all experienced trouble getting them to work correctly. But Flit needs to be able to build a test application not in a single way, but under any given compilation with any of the supported compilers, and also execute their tests and collect results. So any unexpected failures or any variability in its execution may potentially lead to silently creating unreliable or incorrect final executables. So if we have mislabeled executables, then the user may take action that is not well guided by the tool. So misleading their action on their own application. So one of our goals with Float and supporting such tool is to make the activities of this kind of search more transparent to the user and give measurable metrics for them to understand the execution of a tool like Flit. And then giving them more information and interaction with the tool gives them more knowledge of the process and also the ability to dispatch the work and apply the tool in a more intelligent way. For example, real-world examples, even after targeted development to optimize Flit to apply to a specific large code base, these tests can still take multiple days, recompiling large applications and re-executing tests on them. So any bit of information that the user can use to target their application of such a tool is helpful for them. So the next question might be, what about other standard kind of profiling tools to direct such development? Why reinvent the wheel? So we feel that standard profiling tools are somewhat specialized to handle programs in a traditional environment. So for example, they may be programming language specific, architecture dependent, or they generally are implemented with a specific methodology like source or binary instrumentation, etc. Whereas in high performance computing applications, we need more flexibility of these tools. In HPC applications, the performance and memory bottlenecks are often very tight. A tool that is instrumenting this application to measure certain quantities needs to often be able to adapt to these bottlenecks to avoid crippling the program and being unable to be used. Many of these HPC applications conflate different systems and languages For example, FLIT is written with 3 different programming languages that interact, comprising different elements that FLIT offers. And it also supports FLIT can analyze different other languages outside of these 3, other applications written in these other languages. And then these kind of program analysis tools specifically, of course, can be implemented with any number of methodologies like binary instrumentation, LLVM passes. And these may sometimes conflict. If a profiling tool and some tool like some other meta tool like FLIT are both achieving their goal with binary instrumentation, then there's no guarantee that the instrumentation doesn't conflict and that these calls aren't affecting the operation of one tool or the other. So I want to briefly go ahead and discuss our actual initial design of Float to analyze FLIT. So our initial goal is to represent the FLIT model in a high-level abstract system, which in particular hides the complexity of having hundreds or thousands of individual compilations. Even if you only have 100 different compilation settings, each file within the source application has to be compiled this way. So we can represent the execution of a FLIT on any application with this handful of events that are comprised of kind of some sort of arbitrary set of actual code activity and function calls happening under the hood within the events. The events are defined in a very simple way. The user just needs to implement. We instrument manual log calls in JSON format that we can collect later and connect. And so we can determine any amount of information that we need to capture to make our use of the tool helpful in our given situation. And then we can define dependencies between these events as shown. So of course, in the case of things like a tool like FLIT, where we're compiling and linking many different versions of an application, we need to capture a lot of information on what compiler was used, the optimization level, the switches used for this compilation, and the files involved, etc. And then, of course, if we want to, in particular, track runtime, we can measure runtime at each of these steps, and we can measure any other data that we are interested in collecting. So given this user-defined relationship and these user-defined events, we can get automatically out of Float a dependency graph like this on the left, which I apologize, it's difficult to see as is, but we'll zoom in here to some parts. But this represents a very simple event, which highlights the need for simplifying and narrowing down the scope of visualizing such executions. This is a very simple test case of FLIT for demonstration purposes with only a handful of compilations and tests. In a real-world scenario, there might be hundreds of files and or hundreds of compilations, creating a very unwieldy set of data to analyze. But narrowing down, in any way you might normally analyze such a DAG, narrowing down to, for example, this subgraph comparing the longest running branch against a baseline branch helps us compare certain file differences. Did specific tests take longer to run in one than the other? Or can we look at the captured data and determine why in one branch this event took longer than in another? Also, another view that we used in our initial analysis was a simple Gantt chart, also just a view of their dependencies and relative runtimes. This particular chart shows the result of running the makefile component of FLIT with a 4-job cap on simultaneous jobs as compared to running with unlimited jobs, for example. We can see when each event is stopping and starting and infer some of their dependencies. And from here, also, we were able to identify pretty quickly an implementation bug in the in FLIT by identifying some excess compilations of events by determining the relation between some of these dependent events, and we were able to not only see that there was a specific compilation being repeated unnecessarily, but identify kind of what the cause was based on what dependencies were forcing it to be regenerated, which saved quite a bit of time and really helped with the runtime of FLIT on future tests. So what did we learn? Focused use of tools like this for a very narrow domain really was helpful and seems quite important for such applications. These applications are becoming increasingly heterogeneous, running on many different types of hardware simultaneously, many different languages, and the ability to mold our visualizations and be able to analyze at a more custom and designer kind of abstract way is very helpful. And then we have, it becomes possible to take a newer acceptance criterion. So for future work, we're in progress working on a GPU adaptation of FLIT, and as a result, and also simultaneously of float, where visualizing the execution of events within FLIT while applied through GPU kernels. These visualizations help us understand and optimize the use of the resources that we have. We hope to make these visualizations, offer more visualizations, more interactive querying of the data, and in a lot of ways this can inform FLIT to automate itself in a more intelligent way and increase its own performance. And that's all I have. Thanks very much. Hello.
All right, so thank you. I hope John is online. All right, hi, welcome.
Hello.
Okay, are there any questions from the audience here? I haven't seen any on Slido. There's one here.
Hello, thanks for the nice presentation. That's very interesting, especially my background is in augmented reality and all these real-time systems where floating point operations tend to be a crucial thing over there. So you didn't talk specifically about what kind of applications. For example, if you look into some tracking systems, augmented reality or Unity or Unreal Engine, can this analysis be used for builds, like for devices like HoloLens or some VR headsets or augmented reality smartphones, for example, like LiDAR iPads, because there's a big variety of all sorts of ARM CPUs and all that things. Thank you.
Yeah, so the FLIT application is pretty much generally applicable to any software, and the main driver of creating the kind of beginnings of this visualization to accompany it was because basically, it's a small kind of new tool. We're trying to increase adoption. So the initial uses were some fairly large numerical scientific computing applications at Lawrence Livermore National Lab. There have been some others. We've worked with some folks at another lab on weather simulation, weather modeling. So FLIT is pretty much black box, applicable to anything. And the main point of visualizations, which there have been more added since, I think, is to sort of help estimate the load, since it is generally most useful in large applications. And so guiding the test usage so that you can get a reasonable test time is helpful and help increase our adoption at Livermore a little bit.
Okay, thank you. Are there any questions from here? Maybe I have one. You showed for your workflow visual representations, kind of the curved node link diagram, but also a Gantt chart. Well, you explained a little bit what you can see in the Gantt chart, but what was your take on or methodology in choosing the different visualizations, and have you tested out others as well? Of course, we've used such visualizations for similar applications before, but can you shed any kind of light on specific requirements in your case?
Sure. We did test a couple. I mean, obviously, these are all pretty rudimentary, and we tried other simpler things. So the use case in particular that we started with was essentially understanding, I guess it was twofold. One, in sort of understanding the performance model of FLIT itself, because the applications that it's used for, as I mentioned, are quite large. You know, compilation of some of these applications can take hours. Running them sometimes can take hours, maybe both or one or the other. And driving the development of the tool, we wanted to understand a little bit better where the time was currently being spent. But then also it was helpful for, I guess, understanding what the tool is doing and how it works. So a lot of it was just mostly the ones presented here that we kind of ended up using and stuck with were used to represent and understand the sort of actual underlying behavior of the program, what sort of tasks are running at what time, what kind of concurrency we have, and also to understand the actual like sort of abstract model of what's going on in FLIT. A lot of the kind of people leading the FLIT project even didn't really have a great understanding of how the flow of the tool fit together, where linking and compilation steps were happening, what the dependencies were between different events, like running and comparing different test results. So that was kind of the main reason for these specific visualizations at the time.
All right, thank you. I don't see any other questions left here, so let's thank you and the other presenter of the session again.
Thank you.
And we're almost done, so welcome Steffen back onto the stage.
Yeah, so we have basically reached the end of this workshop. And I would like to thank again everyone who contributed to it, the keynote speakers, the authors, the presenters, program committee, and also, of course, the WIS organizing committee, and last but not least, you, our audience. Thank you very much for being here, either on site or online. Please do not forget to go to testvis.gitlab.io and fill out the questionnaire. That would be very kind. So we get a little feedback, and with this, I would like to close the session. Please feel free to reach out to us if you have any questions or are interested maybe in getting involved, organizing another workshop on this topic, etc. Thank you very much.
The tech chairs and the SVs.
The tech chairs and SVs, I forgot them. Oh, sorry. Thank you so much.